So welcome everyone. I'm going to start today's lecture recap with, as usual, a quick discussion of what we were talking about last time. And so last time, what we were interested in, we were talking about the first law of thermodynamics, the various ways that energy can be transferred from our system to the environment. And so in addition to the heat transfer that we spent quite a while on, we understood that you could have some energy transferred through a mechanical process. For example, when a gas expands against a piston, which is moving outward, then there's some energy that's transferred to the piston in the environment through the force pushing on the piston. That's what we call work. So work is energy transferred through mechanical processes. And we understood that in order to write our energy conservation equation in general in these kinds of processes, we need to take into account the work. And so we have this very simple equation that says, if I want to know how much the energy of the gas changes during a process, so the actual energy of the gas molecules, that's the change in what we call U, then I can say that's equal to the amount of energy that goes into the gas by adding heat, that's Q, but then I have to subtract any energy that's transferred out of the gas through these mechanical means. Okay, so that's W. And so this equation just expresses the conservation of energy. It's valid regardless of whether heat is going in or out, or whether the gas is doing positive work on the environment, or the gas is being compressed and it's actually receiving energy through mechanical means. Okay, it's just taking into account the different signs. So in some cases, Q is going to be positive. In other cases, Q is going to be negative. Same thing with W, but this equation is always valid. Okay, and so one thing, for example, that it allows us to predict would be the change in the temperature of the gas if we have a certain heat added and a certain work being removed. And we'll see, I'll review again that this delta U is directly related to the change in temperature. So first, let's review what we said about calculating work. So the general formula for work, in any case, regardless of whether it's a gas or a person pushing on something, what we want to look at is the force that is being exerted on an object, multiply that by the distance the object moves in the direction of the force. Okay, so if those are in the same direction, we take a positive delta X. If it's the opposite direction, it's a negative delta X. In the case where we have a gas, we can rearrange this formula. So if you have a gas and a piston, then we can rearrange this formula by dividing the force by the area and multiplying the delta X by the area. And then we get this nice general formula that says the work done by a gas during a process is equal to the pressure of that gas times the change in volume of the gas during the process. And so this formula emphasizes, it makes it very clear that if the gas is expanding, then we're going to do positive work. So the gas is pushing on the walls of the container. If those move outward as a result, then the work is positive. If the gas is contracting, if the change in volume is negative, then that corresponds to negative work. Okay, so in this case where this person is pushing on the gas, then the work done by the gas is negative. That means the gas is actually gaining energy rather than giving it up. So we understood that this formula is applicable if the pressure is constant during the entire process. Many situations have the pressure changing from the start to the end. And then we have to think a little bit harder about how we're going to calculate the work. And the solution that we came up with in the case where the pressure is actually changing is to still use this formula, but to break up the process into many steps, where during each step, the pressure is approximately constant. So that's what's indicated here. So we said that occasionally it's useful to plot one of these processes on a pressure volume graph. So we're just looking at the pressure and the volume at all of the points through the process and then showing how that changes from the start to the end. Okay. And so what I mean by breaking up the process into a bunch of little steps is that we consider the part of the process here where, say, the volume changes from 30 liters to 31 liters. And during that part of the process, the pressure is approximately 50 during the entire time. Okay, so the shorter I take the step, the less the pressure changes. And then in this case, for that first step in the process, we can calculate the work using the formula P delta V because pressure is always about 50. And then we move on to the next step in the process and calculate P delta V again for this next step and for the next step and for the next step. And so for each of these individual steps, the pressure isn't changing very much. That sum of works for all those different steps has a nice geometrical interpretation because P delta V for each of those steps is just the area of one of these rectangles on the pressure volume graph. Okay, so P is the height, delta V is the width. And so when we break up the process into many, many steps, calculate P delta V for each one and add them up, that's equivalent to adding up the areas of all these rectangles. And in the limit where the rectangles become infinitely thin, just infinitesimal width, then in that limit, our calculation gives us exactly what the work is, because then the pressure essentially doesn't change at all during any of the individual steps. Okay. And so our P delta V formula is accurate for each step. Adding it all up gives us the area of these sort of infinitely many rectangles, and that adds up to the exact area under the graph of pressure versus volume. Okay. So that's the final result, that when the pressure is constant, you can use this formula. When the pressure is changing during the process, that same formula applied a whole bunch of times tells you that the total work is the area under the curve on this PV diagram. And it doesn't matter if it's a straight line or a curved line, it still works. The work is just the area under the curve. Okay. That's for the case where the volume is increasing. Okay, so that was positive work. In this case, we see that the original volume is less than the final volume. And so we calculate the area, and that positive number is equal to our work. The other situation you might have is a process where the volume is decreasing. So if I drew the arrows the other way on this diagram, then you would have a decreasing volume. You would expect a negative work, and it's still just the area under the curve, but with a negative sign. So mathematically, that area is what we call the integral from the initial volume to the final volume of P of V dV. Okay, so that's the meaning of the integral. The definition of the integral is even using these rectangles and they're taking this limit where the rectangles are infinitely narrow. Okay, so that connects up with integral calculus. We won't really be using the techniques of integration very much in this course, but it's good to know that this is sort of an application of integration. And I guess at least next term in math, you'll definitely spend a lot of time working with expressions like this. Okay, so that was our review. I want to give you a question now to think about that's related to work. And this is an interesting question because there's a few different kinds of work going on. Okay. And so here we have a gas in a cylinder. It's just a regular environment. The person is pulling on the piston in order to make the gas expand. And we want to know what kind of work is being done by the gas. Is it positive or negative? What about the person? Is the work done by the person positive or negative? And then the extra part, is there anything else doing work here? So take a few minutes to think about that. Stop the video, and then we'll talk about this. Okay, so let's have a look at this situation. So we have our gas, and we have the person pulling, and the initial situation is like that. And in the final situation, the gas has expanded. So first, let's think about the work done by the gas. And so here, we're always able to say um, that we're talking about, if we're talking about an increase in volume, then we're going to have positive work. Okay, so maybe we don't know whether the pressure is changing or not. Probably it's decreasing, but at every step of this process, the volume is increasing, and so every contribution to the work done by the gas is going to be positive since the volume is increasing. Okay, so the work done by the gas is positive. What about the work done by the person? So then we can use our general understanding that if you're exerting a force in one direction, in this case upwards, and if the thing that you're exerting a force on moves in the same direction that you're exerting the force, then the work is going to be positive. So we say the work is F and delta X parallel, or delta X in the direction of the force. And so this is also, so the work for the person is also going to be a positive value. Okay. And so for this question, the answer is B. The work done by the gas and by the person are both positive. Okay. So this is a little bit confusing maybe, because what that means is that the gas is giving up energy, is losing energy because it's doing positive work. Okay. The person is also giving up energy. So it's transferring energy to away from the person, transferring energy to the system by doing this positive work. And so I think it's a little bit confusing at first to say, where is the energy going? Um, One place the energy is going is that the potential energy of the piston is increasing. But we could imagine the same situation where everything is horizontal. And so now we're pulling out on the piston. The work from the gas is positive. The work from the person is positive. But now the energy of the piston is the same before and after the process. Okay, we're assuming it's stationary before, stationary after. It's the same potential energy because the system is horizontal. So where is all this energy going? That is, the energy done by the gas inside and the energy done by the person. Okay. So the answer is that there's also work done by the gas outside the cylinder. Okay. So we should take that into account as well. So there's this F of the gas outside. I'll call that the W from the atmosphere. Okay, and that one is going to be negative, because in that case, the work from the atmosphere, the force from the atmosphere is downward, but the motion of the piston is upward. So those are in opposite directions. And so we're going to have a negative work done by the atmosphere. Okay. And in this case, we can understand that in the horizontal situation, where the energy of our piston is not changing at all, then it must be that the total energy added to the piston from all these different works must add up to zero. So the work from the gas on the piston plus the work from the person on the piston plus the work from the atmosphere on the piston is equal to zero. In this situation where, in the horizontal situation, where the energy of that piston is the same before and after. Or even in the vertical situation, in a limit where the mass of the piston is very small and we could ignore it. Okay. Or if there's no gravity, similarly, the energy of the piston itself is the same before and after. Okay, so that was that. And so that's a nice question, thinking about work and various ways of computing it. Now we're going to move on to a quick review of another term in the first law of thermodynamics equation, which is the energy of the gas. Okay, so kind of summarized this last time, just to review the energy of the gas. It's specifically talking about the actual energy of all the molecules of the gas. And so that could be kinetic energy, it could be rotational energy, it could be vibrational energy, or potential energy. If your gas is not an ideal gas and you take into account the attractive forces or the repulsive forces between the molecules. So you add up all of those sources of energy for all of your molecules, and that's what we mean by U. If we want to calculate U, so the main thing we're going to end up doing is looking at the change in this internal energy and relating that to the change in temperature. Okay, so if you remember from the early part of the course, then if you want to change the temperature of a gas, you have to change its energy by a certain amount, and that proportionality, the proportionality between the change in energy of a gas or any other material and the change in temperature is what we call the specific heat. So in the context of gases, it's more common to work with this molar specific heat, where we have the change in energy is equal to the number of moles times the molar specific heat times the change in temperature. And we talked about how the molar specific heat is going to be something that is larger for a more complicated molecule. And the reason is that if you have a very simple molecule, like a monatomic ideal gas, then all the energy that you add to the system is going to go into the translational kinetic energy of the molecules, and that is directly related to the temperature. If you have a more complicated set of molecules, then some of the energy that you put into the system might go into rotational energy or vibrational energy of the molecules, and less is going into the kinetic energy. And so it's harder, it's then requiring more energy to actually change the temperature, which is a measure of kinetic energy. So CV is going to be larger in cases where you have more complicated molecules. In the case where we have a monatomic ideal gas, then we can understand things a little bit in more detail, and we can understand a specific equation for this molar specific heat. So in that case, all that U is just the total kinetic energy of the molecule. So that's just the sum of a half mv squared over every molecule in your system. And we could alternatively write that as the number of molecules of your system times the average kinetic energy per molecule. Okay. So starting from that, which is an exact equation for a monatomic ideal gas, we can remember that the average kinetic energy per molecule is equal to the temperature times some constant. And the number of molecules is equal to the number of moles times some constant, Avogadro's number. And so we can write a formula for the total energy of our gas as just some constant times the number of moles times the temperature. Okay, so in that case, we can actually derive this relation between U and temperature. Then we get the change in U would equal this constant times N times the change in temperature. Okay, so, and that's the kind of formula that we had here. In this case, it's actually possible to derive an exact expression for this constant starting from the ideal gas law. I won't do that here, but you can also think about just doing some experimental measurement relating energy and temperature to measure this constant. And it turns out that it's just equal to 3/2 times the ideal gas constant R. Okay. So for this very special case of a monatomic ideal gas like helium gas, For example, you have simply that U is equal to 3 halves R times N times T, or delta U is equal to 3 halves NR delta T. Okay. So in that one situation, we kind of know exactly what the molar specific heat is. In all the other situations, what we're going to expect is that we have a larger molar specific heat. Okay, so you find for diatomic molecules like oxygen or hydrogen gas, molecular hydrogen gas, then the CV turns out to be around 5 halves R. And for more and more complicated molecules, you're going to get a larger and larger CV because you have more and more kind of possible vibrational modes of your molecule that can store some of the energy. Okay, so let's have a question related to this internal energy. And what this question has to do with is a very special kind of gas process where we start out with a gas in half of a box. There's a partition in the middle, and on the other side, we just have vacuum. So there's nothing on the other side. And the question is, if I at some point instantaneously remove that partition. So if you just imagine all of a sudden a partition disintegrates, or I'm able to instantaneously slide it outwards so that now the gas is allowed to freely expand through the box, then the question is, what is going to be the temperature of the gas after it expands and fills the box compared with the original temperature? Okay, so take a few minutes to think about that. Think about the definition of temperature and what would happen with the molecules. And then we're going to talk about that now. All right. So this is an interesting question because at first you might think, well, we should look at the ideal gas law or the first law of thermodynamics. But it turns out that the simplest way to understand this question is actually just to think about the microscopic physics and the definition of temperature. So the microscopic physics is that you have just all of these ideal gas molecules bouncing around on the left side of this container, and each of them has a velocity and a kinetic energy, and there's some average kinetic energy of these molecules that is equal to their temperature up to some constant. Now what happens as I remove the partition? Well, all of a sudden, there's a larger volume that these gas molecules can move in. And so some of the molecules that would have hit the partition and bounced back, now they keep going into the other side. And so very quickly, the gas molecules are now going to spread out through the entire container. What happens to the energy of those gas molecules? Well, nothing really. If I have a molecule and it now goes to the other side, its energy doesn't really change. It's going to be the same as it was before, just keeps flying over here to this side. When it bounces off the wall, now it has the same energy after the collision, assuming that, here we're assuming that energy is not being transferred out of the system, that there's no heat that's leaving the box. Okay. So the average kinetic energy of the molecules, it's basically going to stay the same as it was before. And so because temperature is just the average kinetic energy of the molecules times some constant, we can say that the temperature of the gas in the final situation is the same as the temperature of the gas in the original situation. Okay, but what about the ideal gas law, and what about the first law of thermodynamics? What would those tell us in this situation if we tried to use those? So ideal gas law is going to say that, well, it says PV equals nRT. V is definitely increasing in this case, but we can't really conclude anything from that because we don't know about pressure. And so we can't really use the ideal gas law to calculate the final temperature. What we can do in the end, now that we've realized the final temperature is the same as before, we can make the prediction that the pressure in the final situation has to be half of the pressure in the original situation, because the volume is double and the temperature is staying the same. How do we understand this process using the first law of thermodynamics? And so we have that delta U equals Q minus W. And so if we want to see if there's a change in temperature, we can ask, is there a change in energy? Is there a delta U here? And so in this case, we know that Q is equal to 0 because we're not adding any heat to the box or taking heat out of the box. But it turns out W is also equal to 0 because instead of having the gas push a piston outward, exerting a force on the piston and therefore doing work on the piston, we're simply removing the barrier. And so now the gas is just freely expanding into the vacuum. So it's not really pushing, it doesn't really have anything to push on or do work on. And so in this case, W is 0, even though the volume is expanding. Okay, so it's a little bit confusing because that's not mostly the situation is going to be that we actually have a piston that the gas is pressing on when a gas is expanding. And so there would be some contribution to W. In this case, it's a very special situation that we call free expansion, where the gas actually doesn't have anything to do work on. Okay, so that's pretty much what I wanted to say about this question. There's this little extra part about what if it were a real gas with attractive interactions between the molecules? So in that case, what we would have is a potential energy associated with that attractive interaction. An attractive interaction means that if you take the molecules further apart, there'd be a higher potential energy. And if the molecules are closer together, there's a lower potential energy. So they would prefer to be closer together. And so in this case, if the gas expands through the box as it would, then the potential energy of those gas molecules is going to go up because we are assuming the interactions are attractive. Energy is conserved, and so the kinetic energy of the molecules must go down. And so that means the temperature in the real situation with a real gas would be expected to be lower after this free expansion. Okay, and that was just, again, summarizing that the final temperature in this case is the same as the original temperature. So here's another question related to the change in internal energy. We've got a PV diagram. We're going from some process A, from some initial situation A to a final situation B, but we're imagining that that could happen through any one of three processes. So what's different about these processes is that the pressure is changing in different ways. Okay, we have some initial volume and some initial pressure. Maybe I'm pressing down on a gas in a cylinder with my hand, and then I gradually let up, and so I release the pressure, but I could do it uniformly, or I could actually press down a little bit and then up and then down, or I could let it up really quickly, but then press down a little bit at the end. So there's various ways that I could imagine having the gas expand with different changes in pressure during the process. And the question here is, for which one of those different ways indicated by the three paths on the PV diagram is the change in internal energy going to be the largest? So think about that for a minute based on what you know about internal energy, and then I'll talk about the answer. Okay, so let's talk about this question. The answer in this case is D, that the change in internal energy is going to be the same for all of these three different paths. So how do we understand that? We can basically just appeal to our formula for delta U. So delta U is always given by N times CV times the change in temperature. And so what I'm going to argue is that the change in temperature is the same for all the three paths from A to B. And basically that's because if I know the volume and I know the pressure, then I can calculate the temperature by the ideal gas law. So we're assuming here that the number of moles of gas is the same in all the processes. The gas is contained in some cylinder. It doesn't change the number of molecules. And so basically there's some pressure and volume at the start, and so I can calculate the temperature at the start. There's some pressure and volume at the end. I can use the ideal gas law to calculate the temperature at the end. And the change in temperature then doesn't really care about which path I take from the start to the end. The only information I needed to know to calculate this delta T was the initial pressure and volume and the final pressure and volume. And since those are changing in the same way in all the three processes, then we're going to get the same change in temperature, and so the same change in the internal energy. Okay. So the change in internal energy is path independent. I want to contrast that to the other things in the first law. So the work, of course, it is different for all these paths because the work is the area under the path. The work for path number 1 is going to be the largest because it has the largest area under the path. The heat also must be different for these three paths because if the change in internal energy is the same and delta U is Q minus W, then Q must be different for the three cases, must be larger in the case where the work is larger so that so that delta U can actually be the same. Okay. So that's that. Just a little bit of jargon for you. The fact that U is a property that can be calculated once I know, or is determined in principle once I know the pressure and the volume and the temperature and the number of moles. We say that U is a state variable. Okay, so whereas W and Q are sort of amounts of energy that are transferred in a process, and we need to know the process to know what W and Q are. U is simply it's something like pressure, volume, temperature, number of moles. It is just the energy of the gas in a certain configuration. And so when we have delta U, all we need to do is say that that's the U at the end minus the U at the beginning. And so that's another way of understanding why we don't really care what the process is, that delta U has to be the same regardless of the path we take from the initial to the final state. Okay. Okay, so I think I'll save this one for next time. Just a quick look ahead. Okay, so what we're going to be doing now, having understood the ideal gas law and this first law of thermodynamics and the definition of work and the definition of internal energy, we're now actually at a good point where we can analyze all sorts of interesting thermodynamic processes. And so these are going to be processes that are applicable in real useful, situations like engines and refrigerators. So just to give you an idea of the kind of thing we'll want to do, we'll want to maybe analyze in a certain machine. So let's just see this example here. I've got a little animation where what I'm going to show you is something called a heat engine. And it's just a way of taking heat and turning it into work that we could use to do something useful. So here's on the right some hot reservoir that we're keeping hot somehow. On the left, there's some cold object that we're keeping cold somehow. In the middle, there's a gas in a piston, and we're going to make this gas do some work for us. Okay, and so the way that we're going to do it is we put it in thermal contact with our hot object so that it heats up. Now we release the piston so that it can expand, and it continues to take in heat from the hot object as it expands. At some point, we close that off and now put it in contact with the cold object. And So we'll fix the volume, let it cool down. Now we'll release the piston so that it can contract. Okay. And close it off again, expose it to the hot object, and now heat will flow in, and we're actually back to where we started. Okay, so there's various cyclic processes like this where what we find what we want to do is analyze these kinds of situations. Okay, that was just some arbitrary process that I made up. Well, it has a name. It's called the Stirling cycle. What we want to do is understand if we do something like this, are we actually going to get some useful work out of this? In that whole process, does the gas do some net work on the environment? Okay, and if it does, then that's useful to us. Okay, and so we want to do things like calculate the work for each part of the process, and then in the end, we want to calculate what is the total work that the gas does during that process to see how much how much we could do with this particular system, which is called a heat engine. Okay, so we could calculate the total work using the methods that we've talked about today in last class. The other thing we might be interested in is how much heat do we have to supply in order to do this work? Okay, so the reason we're able to have the gas do some work is that we're supplying heat to this side and cooling down this side. And so we want to know how much heat do we have to supply if I want to get 1,000 joules of work out. That's related to what we call the efficiency of this particular heat engine. Okay. And in order to do those calculations of heat, we're going to be using the first law of thermodynamics. We're going to need to figure out what the temperature and the volume and the pressure is at all the different steps of this process. And so that will use the ideal gas law. Okay. So using ideal gas law, our formula for work, our first law of thermodynamics, and our formula for what the change in internal energy is, we're going to be able to analyze all these possible processes that you could imagine and analyze a lot of useful things like the efficiencies of engines and refrigerators. Okay. So next class, what we're going to do is kind of focus on these individual steps that might take place in various processes. So specifically, we'll look at constant volume processes, constant pressure processes, constant temperature processes, and processes that we call adiabatic, where no heat is transferred in and out. And then we'll be sort of understanding how to analyze each of those and calculate all of the relevant thermodynamic quantities. Okay, so that's it for today, and we will see you on Friday.